Hello there. This video is on finding inflection points of a function. In the previous video, I showed a vocabulary page just to make sure people had in their notes some of the new vocabulary if they're not familiar with it. So concave up is a graph is shaped like this where it goes upwards, it bows this direction. It can be half, that's still concave up, doesn't have to have both halves. So anything that bows up like this is concave up. Anything that bows down, either one half or the other half or both halves, that's called concave down. And where it switches between concave up and concave down, where it switches between the concave up and concave down, is called an inflection point, or vice versa, concave up to concave down this way. All those kinds of things where it switches concavity is called an inflection point. And then I have a little summary here. The way we're going to do our analysis of functions is we're going to find all the critical points. Critical points could be a local max, a local min, or inflection point. It's got to be one of those three. And then we're going to take the second derivative and use it to find any possible additional inflection points. We do that by taking the derivative equaling, or the second derivative equaling 0 and the second derivative undefined. Those will give us possible additional inflection points. And that's kind of our approach at analyzing these functions. All right, so let's get down to an example right away. We did an example in the last video of searching for inflection points. We found an inflection point at x equals 3. So I'm going to do a similar example. We're going to be searching for maximums and minimums and also inflection points. All right, so what's our process? Our first step is to find any critical points, try to classify those. And then our next step is to find any possible additional inflection points by using the second derivative. All right, so take you through the steps. Step number 1, we're going to find the critical points. How do you find critical points? Well, the derivative is equal to 0 or it's undefined. So first I have to find the derivative, and then I have to find out when it's 0 or when it's undefined. So my derivative, here's my function. So my derivative is just using those shortcut rules that we learned last chapter. So there's the derivative of x cubed minus 6x squared plus 12x. And then I need to find out when that's equal to 0. Or I need to find or I'm not sure what the proper conjunction is, but we also need to find out when it's undefined. So 12 is undefined. I guess this line's in the way. Go away, line. So undefined. Okay. So let's use some algebra here. Let's see. This guy can be factored. And we'll get that in a second. I think this can be factored some more. Let's find out. X squared minus 4x plus 4. I think that's x minus 2 times x minus 2. We need to double check our factoring because it's just a guess and check process. So 4, yeah, that works out. So if you need to check it by hand on paper, that's good too. Just make sure you check it, whichever way you want to do it. This means we either have the first guy equaling 0, which is not possible. We have the second guy equaling 0, which is definitely possible. Or the third guy equaling 0, which is the same answer as the second one. So this is not possible. Here we get x equals 2. And this is just a repeat. So no new information. So x equals 2 is called a critical point. And that's a very important point for us. It could be local min, local max, or a point of inflection. All right, we also need to find out when the derivative is undefined. So when is 3x squared minus 12x plus 12 undefined? It is never undefined. How do I know? Well, I know a lot of math. Specifically, I know a lot of precalculus. I know that this is a parabola, 3x squared minus 12x plus 12, and parabolas don't, you plug a number in, you get a number out, right? There's no undefined values. When I plug in x equals 4, I get an answer. I don't know what it is, but I know I get an answer. Also, I can say I never divide by 0. I never have a square root of a negative number. The classic things that we can't compute can't exist in this function because we have no division, so we can never divide by 0. We have no square roots, so we can't take the square root of a negative number. We have no logs, so we can't take a log of a negative number or log of 0. So none of those things happen. So we know this function is never undefined. This derivative function is never undefined. So we have one critical point, x equals 2, and we're going to classify that. One way I've been trying to emphasize classifying this is by looking to the left, looking to the right. We are going to learn a more sophisticated method that sometimes works. So I don't know how more sophisticated you want to call that, but we're going to learn how to use the second derivative to help us classify these as local mins, local maxes. It doesn't always work, but it's oftentimes helpful. So we're going to learn that method as well. So x equals 2 is our mystery point. We don't know what that is. So we're going to look a little bit to the left, and we're going to look a little bit to the right, and we're going to try to see if it's increasing or decreasing on either side, and that will help us determine whether it's a max, a min, or inflection point. So I can choose any point I want on the left, like I can choose 1 on the left, because that will tell me if the graph is increasing or decreasing. I need to pause the video because my pen stopped working for a moment. All right, fixed. So I can choose 1 because that's to the left. I'm actually going to choose 0. You can choose whatever number you want, but 0 is just easier for me to compute with. So I'm going to choose a number that's easier to compute with. And on the right, I'm going to choose something like 3. And I'm going to just try to figure out whether the derivative is positive or negative on these two intervals, on the interval with 0 in it and the interval with 3 in it. So my x values of interest are my test points are 0 and 3. And then my derivative is what I'm going to plug it into because I want to find increase and decreasing. I don't want to find y values. My derivative value, if you remember, my derivative function is 3x squared minus 12x plus 12. But you can also write it, if you want, as 3x minus 2 squared, or x minus 2x minus 2. That's the factored form of it. It's equivalent to 3x squared minus 12x plus 12, and it may be easier to plug numbers in. Certainly, it'll be easier to plug the 3 in. So to plug in 0, I'm just going to plug it into this other version right here. I get 3 times 0 minus 2 times 0 minus 2, which is 3 times negative 2 times negative 2. Which is negative 6 times negative 2, which is positive 12. This is a positive number. So I know in this region over here, where x equals 0, the derivative is positive. So we call that increasing. And for x equals 3, I'm going to do 3 times 3 minus 2, 3 minus 2. So that is 3 times 1, which is 3, which is greater than 0. So it's also increasing. All right, well, increasing and increasing is not a local min or a local max. So this has got to be an inflection point. Right? Increasing and increasing cannot be a local max, cannot be a local min. It's got to be one of the three. So by process of elimination, x equaling 2 is a point of inflection. All right, so after we have found the critical points with the derivative equaling 0 or the derivative being undefined, we need to go find possible additional inflection points by using the second derivative. So possible additional inflection points. So how do we find possible additional inflection points? We take the second derivative and we make that equal to 0, or we make it undefined. So our first derivative from above, well, it's off the screen a little bit. Our first derivative is up here, dy dx. It's equal to 3x squared minus 12x plus 12. And I'll just differentiate it again to find the second derivative. So the second derivative is written like this. Funky little way of writing it. 3x squared differentiated is 6x, and then we get a minus 12 at a plus 0. So we set this equal to 0, and we find out when it's undefined. So when it's equal to 0, well, we just get 6x equals 12, or x equaling 2. So that's also an important point. It's not called a critical point because critical points are when the first derivative is equal to 0 and when the first derivative is undefined. This is a different kind of thing. It is definitely not a local min or local max because we would have already found it, right? From the critical points, we find all the local min, local max. So this has to be an additional. I'm not sure if I need to use the word additional. Let's just call it an inflection point. I mean, yeah, it's an additional one, but regardless of that, it's an inflection point. We found it. We only found it additionally because we searched for it after the other one. Additional, oh no, inflection point. Inflection point. There we go. What about when the second derivative is undefined? So second derivative undefined would be when 6x minus 12 is undefined. 6x minus 12 is a line. Lines are undefined. You don't divide by 0, etc. So this is never undefined. So we don't find any inflection points from this. But we do get an inflection point at x equals 2. And we also had an inflection point from above at x equals, oh, it's the same darn one. Look at that. So this is why we call it possible additional inflection points, because we got 2, but we already knew it, right? So just because the second derivative is equal to 0 doesn't guarantee that we find any new information. If x equals 2 is already a minimum, it's not going to change. We've already found it. If x equals 2 is already a critical point, it's not going to change, right? So no matter what, we still find the same information as we did before. Only additional things can we find using the second derivative. Let's go look at a graph of what this is. I'm curious as to what this graph looks like. This is x cubed minus 6x squared plus 12x. Let's see, it's over here. Oh no, here it is, right here. Oh yeah, I looked at it before the video started, so I just forgot it immediately. All right, so here's the graph. It's increasing. It has a little plateau here, and then it's increasing. And that is what we discovered before. Remember, it's increasing, and then it does something interesting, and then it's increasing. So this is what the graph increasing. It does something interesting called an inflection point, and it's increasing. Let's talk about concavity. Do you see how this kind of bows downward? This is a downward sloping thing on the left-hand side. So this is the inflection point. So look to the left of that, and that is concave down. And if you look to the right of it, it's concave up, right? So this part on the right-hand side over here is concave up. It goes upwards. Not the graph itself, but kind of the turn of it. It turns up, and this thing is turning down. In terms of derivatives, right here, the derivative is a bigger number and then a smaller number, and then eventually the derivative goes to something like 0. So the derivative is decreasing, and over here the derivative is getting bigger. So the derivative starts at 0, the derivative gets bigger, like at 1, and then 2, and then 5. So that's how officially concave up and concave down are defined in terms of whether the derivative is getting bigger or smaller. But I find that most Calc 1 students don't really like that definition as much as sort of the bowing of it. It bows sort of in a downward shape, like an N, that's concave down, or bows in an upward shape, that's a concave up. All right, and there are no max and mins. We can zoom out if we want, but we know because we did the calculus that there are no maxes and mins. There's no local max, local min, because we would have found them using the first derivative, using finding the critical points. All right, so that is the classification of all the local max, local min, and inflection points for this example G right here. All right, next page. Let me zoom in a little bit so it's easier for us all to see, especially those with smaller screens. All right, so as I mentioned previously, there's a way of trying to classify our critical points as local min, local max, or inflection points without using the increase and decreasing test, making a little table and testing whether it's increasing, decreasing. That can seem a little burdensome in terms of like how tedious math can be. So we have another way of doing it. It's called the second derivative test. And they call it the second derivative test is because we use the second derivative to test the critical points, right? So the test is only going to be used on critical points. We're trying to test the critical points. So here I have it written out here. This test is used to help determine if a critical number, critical point, is a local max, a local min, or we don't really know, something, possibly something else. So here's the problem with the second derivative test. It doesn't always give a definitive answer. If we take the second derivative and plug in a critical number, critical point, right? If we take the second derivative and plug in some critical point there, and the result is positive, so if it has upward concavity, greater than 0 means that it's upward concavity. Well, what kind of critical point is that? That's a minimum. So if it goes upwards, if the second derivative is positive, we know that at that location, we get a local minimum. And contrary-wise, if the second derivative at a particular point is negative, so that would be concave down, then we know that it has a local maximum. And here's the part where students get wrong a bunch of times, so hopefully you will not get that wrong. When the second derivative is equal to 0, you have no idea. You may think like, oh, well, local min, local max. The other option is inflection point. Unfortunately, if the second derivative is equal to 0, then it could be a local min, it could be local max, could be inflection point. We have no idea. So basically, the way I say this is you wasted your time because you don't know anything. And you need to do something different, which maybe go back to the increase and decreasing thing to see whether that that tested point, which is inconclusive, is in fact a local min, local max, or inflection point. All right, so let's do some practice here. Let's go back to a previous problem we did, or a couple previous problems, and we're going to practice using the second derivative test. So one of them was example A, where we did this problem here before. You can go back and look at example A if you want. Whoops, it's a previous page, so I'm not going to hunt back there, but this is an example that we used before. So we've already done the math for it, and I can show you the graph, and we can see our answer from before. But let's go ahead and see if we can apply the second derivative test. So we got to find the first derivative. We got to find the first derivative equal to 0 and the first derivative undefined. So we need this equal to 0, and we need undefined. And when we plug it equal to 0, we get this factorable quadratic equation. I'm going to go through the steps again, but rapidly, because we've already done this before. So we get x equals 7 and x equals -1. Those are the two critical points. And we got those from when the derivative is equal to 0. We also have to find out when it's undefined. This doesn't look like or undefined. It looks too messy. So let me do this. Maybe do it for a different color. So or undefined. Maybe that's just still unreadable. But so we want to find out when the first derivative is undefined. And if we look at the first derivative, it's never undefined. It's a parabola. Parabolas are undefined. You can find all the points you want there. All right, so instead of trying to classify the critical points using, for example, increasing and decreasing, we're going to apply the second derivative test. All right, so to apply the second derivative test, we need the second derivative. So the first derivative we just found. And I'll find the second derivative. We did this before too, so again, I'll just write down the answer here. And then what we do is we're going to put in each of the critical points into the second derivative. So you can take these and you put them in, you test them in the second derivative. All right, so what does that look like? Well, we take the second derivative, so there's a square there, and you plug in x equals 7. And you take the second derivative, and you plug in x equals -1. And then we use the second derivative test to see if we know their local max or local min. So x equals 7, what do we get? We get, well, here's the second derivative. So we get 6 times the x value minus 18. 6 times 7 is 42. 42 minus 18 is a positive number. According to our second derivative test, if the second derivative at a critical value is positive, that's this one right here. If the second derivative, when you plug in a critical number, is positive, then we know it's a local min. So here we know that x equals 7. So x equals 7 is a local min because of the second derivative test. Let's check the other one here. We're going to plug in -1, which is our other critical point. So again, this is our second derivative equation. So take the critical point, test it with the second derivative. 6 times -1 is -6. -6 minus 18 is -24, less than 0. And as we remember over here, if the second derivative at a critical point is less than 0, we get a local min. So our local max. So, sorry about that, x equals -1 is a local max. I know this because if the second derivative is negative, it's going down. It has that downward shape, and that's a local max, right? So I know that. I just wrote it or thought it the opposite way. All right, so that's using the second derivative to classify the critical points. So let's do one more example of that, just so you can see the second derivative test in action, and then we will be done with today's video. Okay. I guess I'll use green over here. All right, so example B, we have this equation right here, y equals x to the 4th over 4 minus 8x squared. We've done this one before, but again, we're practicing the second derivative test. So let's find the first derivative. First derivative is going to be x to the 3rd minus 16x. And we're going to find the second derivative. We'll do the second derivative right now just because it's on my mind. So the derivative of x cubed is 3x squared, and the derivative of 16x is minus 16. All right, so that is the first and second derivative. I'm going to find out the critical points by making the derivative equal to 0 and finding out when the derivative is undefined. That should be a minus 16x, right? Okay, let me fix that. So we'll just do the undefined real fast. It's never undefined because this is an x cubed graph. X cubed graph is a polynomial graph. It's never undefined. We don't divide by 0. We don't take logs, nothing like that. So it's never undefined. So we don't have to worry about critical points from the derivative equaling undefined, being undefined. But it is possible for the derivative equaling 0. I'll show you how that works. I'm going to factor this one here, x squared minus 16. And the x squared minus 16 can be factored further. And we set each of these guys equal to 0, because when you have a whole bunch of things multiplied to be 0, we know that one of them's got to be 0. Could be more than one, but at least one of them's got to be 0. So each of these will give us a potential value where the derivative is equal to 0. In fact, this one, x equaling 0, gives us a value when the derivative is 0. X equaling 4 is this one right here. So that's a critical point, and x equaling -4. That's another critical point. So we have three critical points. So we're going to use the second derivative to test each of those critical points. So we're going to use the second derivative test. So I'm just going to line up a table here. We have 3 different important x values, 0, 4, and -4. And for each of those, I'm going to plug it into the second derivative to do my second derivative test. So the table is just organizing the information, so it's a little easier to see it all. All right, I'm going to plug in 0. I plug in 0, I get, I plug it into this equation right here because that's my second derivative equation. I get 3 times 0 squared minus 16, which is negative 16, which is less than 0. So it's concave down, so it's a local max. What's a local max? Well, the critical point's a local max. X equals 0 is a critical max because, or is a local max because that was the critical point. All right, let's plug in 4. So we get 3 times 4 squared minus 16. 3 times, well, 4 squared is 16. 3 times 4 squared is 48. 48 minus 16, I'm not good at arithmetic, but I know it's greater than 0. I know it's positive, right? So positive means it's concave up, which has got to be a local minimum. Again, x equals 4 is the local minimum. And let's plug in negative 4. So we get 3 times negative 4 squared minus 16. 3 times negative 4 squared is 48 minus 16, which again is positive. So x equaling negative 4 is a local minimum. So we have three critical points. We know that there are 2 local minimums and 1 local maximum. Let's go check out the picture of x to the 4th over 4 minus 8x squared. It should be up here somewhere because there it is. X to the 4th over 4 minus 8x squared. So let me recenter this and zoom out a little bit. So here's our graph where we have 1 local maximum right up here, and then 2 local minimums over here and here at negative 4 and positive 4. So that was the second derivative test, and how you can, find or at least classify the critical values from there. All right. Okay, so hopefully that video was helpful for you in terms of understanding what an inflection point is, how to find it, how to classify it using the second derivative test. We'll be doing a lot more on inflection points in the next sections to come. Please reach out if you have any questions, and I hope you have an enjoyable day.